Okay, today we are going to problem 10.14. A rectangular opening with sides of length A and B larger than A, defined by x equals to A over 2 and y equals to B over 2 exists in a flat, perfectly conducting plane sheet filling the xy plane. A plane wave is normally incident with its polarization vector making an angle beta with the long edges of the opening. Problem A. Calculate the diffracted fields and power per unit solid angle with the vector Smith-Kirchhoff relation, assuming that the tangential electric field in the opening is the incident unperturbed field. A vector Smith-Kirchhoff relation states that where for the normally incident plane wave, the incident unperturbed field may be taken as below. For the rectangular screen, the surface S1 is the rectangle at the z-plane equals 0, with absolute x less than a over 2 and absolute y less than b over 2, and surface normal n hat equals z hat. The resulting integral is then taken below. And we can yield the E fields equals the duration, like this. Because of the rectangular geometry, this expression is simplest when expressed in Cartesian components. However, if we choose to write k vector in terms of spherical components, we may substitute in the spherical coordinates to obtain the E field in the spherical coordinate. And note that standard sin zeta over zeta diffraction patterns for the x and y directions. The scatter power may be expressed as below in terms of the normally incident power on the aperture. Pi equals E field square over 2z0 times AB. The above then becomes that. And note that for small opening, this reduced to dp over d sigma equals pi over pi square ka over 2 kb over 2 times cosine square theta plus sine square theta times sine square phi plus beta. And problem B. Calculate the corresponding result of the scalar Kirchhoff approximation. According to scalar Kirchhoff approximation, we take phi equals phi 0 exponential ikz and n dot gradient phi equals ik phi 0 times exponential ikz, and hence the Kirchhoff approximation then becomes below. The integrals are identical to the ones performed above. The result is blah blah blah. And for problem B, for B equals A, beta equals 45 degree, Ka equals 4 pi, compute the vector and scalar approximations to the diffracted power per unit solid angle as a function of the angle theta for phi equals 0. Plot a graph showing a comparison between the two results. For the above parameters, the vector and scalar expression reduce to dp over d sigma vector. We can get the two expressions below. The two expressions may be plotted on the same graph, but in fact, they are virtually indistinguishable. To show that the vector and scalar expressions are actually not identical, we may plot the difference, the vector expression minus scalar expression, and we can get a graph below. This difference is entirely dependent on the polarization factors. And these factors are nearly identical in the forward direction. Although the difference gets large of axis, there is so little power there that its difference is essentially unimportant.